Beneath the crystal-clear waters near the Greek island of Antikythera lies a mystery that has endured for over 2 millennia. Hidden in the depths was an extraordinary device, an intricate mechanism often hailed as the world's first computer. Crafted from bronze and once operated by hand, this ancient tool could track celestial movements with remarkable precision. For years, its true purpose remained shrouded in mystery. But with the help of modern imaging technologies and ongoing research, the Antikythera mechanism has revealed secrets that have challenged long-standing assumptions about the technological abilities of ancient civilizations. At first glance, the device seemed like little more than a corroded lump of metal and wood, buried among the remains of a sunken ship. Yet beneath the rust and debris lay a hidden clue, an embedded gear that hinted at something far more sophisticated. This single observation sparked a century-long investigation, leading scientists to question just how advanced the ancients really were. The story began in the early 1900s when a group of sponge divers stumbled upon a shipwreck off the coast of Antikythera. Located in the Aegean Sea, this wreck has since been dated to between 80 and 60 BC. Among the treasures recovered, statues, coins, pottery, was a seemingly insignificant bronze fragment. It wasn't until 1902 that archaeologist Vallejo Staris noticed a gear embedded in one of the fragments, suggesting that it was more than a decorative object. This marked the beginning of a scientific journey into one of history's most puzzling artifacts. Over the decades, researchers sought to uncover the mechanism's true nature. British science historian Derek de Soller-Price was among the first to propose that the object was an ancient analog computer. He believed it could be used to predict astronomical events such as eclipses, based on the movement of the sun and moon. His pioneering work inspired a wave of further investigation. With the advent of technologies like X-ray imaging and computed tomography, scientists were able to look inside the corroded fragment stored at the National Archaeological Museum in Athens. These tools revealed previously hidden inscriptions, tiny interlocking gears, and precisely marked dials that provided new insight into the device's complexity. Subsequent researchers such as Michael Wright and Tony Freeth expanded on Price's theories. Wright, drawing on his experience in restoring antique clocks, constructed physical models that brought the mechanism's functions to life. Freeth's team, on the other hand, used high-resolution CT scans to capture intricate internal structures with incredible accuracy. Their findings confirmed that the mechanism was capable of modeling several astronomical cycles at once. Ancient Greek inscriptions found on the device acted as a user manual, offering instructions on how to set the mechanism and interpret its readings. These texts reference cycles such as the 19-year Metonic cycle and the 18-year Saros cycle, both essential for tracking lunar and solar events. The discovery of the Antikythera mechanism has dramatically altered our understanding of ancient technology. Once dismissed as a simple relic, it is now recognized as a masterpiece of engineering and scientific thought. The sheer complexity of the device, built more than 2,000 years ago, suggests that the ancient Greeks possessed technological skills far beyond what was previously believed. Rather than a curiosity from the past, the mechanism has become a symbol of ancient ingenuity and innovation. In many ways, the mechanism bridges the gap between science, art, and history. Its journey, from the depths of a sunken ship to the bright laboratories of modern researchers, illustrates a story of rediscovery and revelation. Each fragment, gear, and inscription adds to our understanding of how ancient civilizations viewed the cosmos. As new technologies continue to re-examine the artifact, a clearer picture of the ancient world continues to emerge. The shipwreck that housed the mechanism has also been revisited multiple times by underwater archaeologists. These modern expeditions have uncovered more artifacts and details about the ship's cargo, providing valuable context about the world in which the mechanism was created. It is now believed that the vessel was part of a large trade network that spanned the eastern Mediterranean. The ship's remains and its contents offer deeper insight into ancient commerce and craftsmanship, proving that the mechanism was not just an isolated marvel, but a product of a broader, highly developed cultural and technological system. Even more astonishing is that this wasn't merely a decorative artifact, it was a fully functional machine. Once we begin to understand its inner workings, we are left to ponder just how much knowledge the ancients truly possessed. The Antikythera mechanism functioned as an astronomical calculator, using a series of carefully arranged bronze gears to replicate the complex motions of the sun, moon, and possibly the known planets. A hand-cranked gear served as the mechanism's starting point. When turned, it set off a precise chain reaction, transmitting motion through the interlocked gear network. One of the mechanism's key features was a circular front dial known as the calendar ring. Early interpretation suggested it had 365 segments, aligning with a solar calendar. However, later studies revealed the ring contained 354 or 355 holes, consistent with a lunar calendar, which better matched the lunisolar timekeeping practices of ancient Greece. Researchers have so far identified at least 30 distinct gears inside the mechanism. Each gear was engineered with a specific number of teeth, and their interrelations were designed to correspond to well-known astronomical cycles. These gear ratios enabled the device to model the movements of celestial bodies with incredible accuracy, offering the user a way to predict eclipses, track lunar phases, and calculate significant calendrical events. The Antikythera mechanism was carefully designed to track several key astronomical cycles, among which the Metonic cycle, spanning 19 years, played a central role. This cycle was crucial because it ensured that after 19 years, the positions of celestial bodies would realign in a predictable pattern. Alongside this, the device incorporated gear ratios that accounted for other essential cycles used to predict solar and lunar eclipses. These included the Saros cycle, approximately 18 years long, and the Callippic cycle, which spans about 76 years. One of the most ingenious features of the mechanism was its ability to simulate the Moon's non-uniform motion. Since the Moon does not travel around the Earth at a constant speed, the mechanism utilized a pin and slot system within a set of gears. This setup allowed a particular gear, driving the Moon pointer, to vary its speed as the pin moved within the slot, thereby mimicking the Moon's accelerating and decelerating motion as it followed its elliptical orbit. In addition to the Moon pointer, the mechanism featured another pointer called the mean sun, which displayed the current date. Some modern reconstructions suggest the presence of a true sun pointer to more accurately reflect the sun's irregular motion, caused by the Earth's elliptical orbit, though no definitive evidence of such a pointer has been found. Still, the inscriptions on the mechanism, along with the gear arrangement, strongly suggest that it was calibrated to align with both lunar and solar cycles. These inscriptions, written in ancient Greek, were vital for understanding how the device was used. They included instructions and indicated the specific astronomical cycles the mechanism was designed to track. While some of these inscriptions have survived only in fragments, advanced imaging techniques have made many of them readable once again. The texts refer to periods such as the 19-year Metonic cycle and the 18-year Saros cycle, both of which were crucial for predicting eclipses and lunar phases in ancient Greek astronomy. Despite advances in our understanding of the device, its exact operation is still largely reconstructed. There is evidence to suggest that the mechanism may have had additional features, such as pointers for the 5 known planets of antiquity. Although no complete planetary gear system has been found, the design of the mechanism hints that such features might have been part of a more comprehensive system. Whether the Antikythera mechanism was used solely for tracking time or also for displaying the movements of the planets, its design required an advanced understanding of both mathematics and astronomy. The overall function of the device was a brilliant fusion of simple mechanical motion and complex astronomical theory. A user would set the pointers and then crank the handle, which would cause the gears to rotate. In doing so, they could predict astronomical events such as eclipses and determine when the Moon would be full or new. This remarkable ability to forecast celestial events years in advance highlights the inventiveness and scientific knowledge of the ancient Greeks. The mechanism, powered not by electricity but by human effort, demonstrates a level of design that remains captivating in its ingenuity. Recent research has brought new insights into the Antikythera mechanism, thanks to innovative techniques that were unimaginable to early investigators. High-resolution computer tomography, X-ray imaging, and computer simulations have been instrumental in uncovering hidden details of the device's structure. Researchers at the University of Glasgow, led by Professors Graham Wone and Joseph Bailey, applied methods from gravitational wave research and Bayesian statistics to reanalyze the calendar ring. Earlier models suggested the ring contained 365 intervals, aligning with a solar calendar. However, new measurements and statistical models point to the possibility that the ring had 354 or 355 holes, corresponding more closely with the lunar calendar used by the ancient Greeks. Using computer simulations alongside the known positions of the surviving holes, these researchers have refined our understanding of the mechanism, publishing their findings in journals and presenting them at international conferences. Much of this progress was spurred by the work of Chris Budiselic, who set out to replicate the calendar ring. His observations and analysis contributed valuable data that helped drive the research forward. Budiselic's efforts demonstrated that even amateur scientists could play a crucial role in advancing professional studies. Armed with this data, Professors Wone and Bailey, using high-resolution imaging and computer modeling, developed a new reconstruction that challenges previous assumptions about the mechanism's design and function. Another breakthrough came through the use of CT scans, which allowed researchers to examine the internal structure of the fragmented gears in great detail. These scans revealed hidden inscriptions and provided insight into the number of teeth on various gears. The high precision with which the gears were cut has been confirmed, as even small deviations would have impacted the device's performance. By analyzing the alignment and spacing of these gears, researchers have been able to simulate the device's operation more accurately than ever before. Computer simulations have also played a crucial role in assessing the mechanical integrity of the Antikythera mechanism. Researchers built detailed models, accounting for factors like gear tooth shape, corrosion, and wear over time. Surprisingly, the simulation suggested that, had the mechanism been used in its current state, it might have become jammed after only a few months. While some of this behavior can be attributed to the effects of corrosion over the centuries, these findings provide further insight into the limitations of the mechanism's design and the challenges it would have posed to its users. The careful craftsmanship involved in the original manufacturing of the Antikythera mechanism has been highlighted by modern research, showcasing the extraordinary skills of ancient Greek artisans. International teams of researchers, drawing from diverse fields such as astronomy, engineering, and history, have collaborated to create new models of the mechanism. This interdisciplinary approach has merged the latest CT scan data with traditional archaeological analysis, leading to significant advancements in both physical and computer-generated reconstructions of the device. These new models not only clarify the mechanism's original design but also offer profound insights into the scientific understanding of ancient Greece. They demonstrate that the Greeks possessed a detailed, practical grasp of astronomical cycles and the complex mathematics needed to model these phenomena mechanically. This newfound knowledge bridges the gap between ancient observational techniques and modern computational methods. The discovery reinforces the idea that the Antikythera mechanism was not just an ancient artifact, but a sophisticated astronomical calculator, embodying a blend of art, science, and engineering that continues to inspire contemporary researchers. Public interest in these breakthroughs has been overwhelming, with documentaries, museum exhibits, and films celebrating the mechanism as a symbol of ancient ingenuity. The collaboration between independent and professional researchers is now hailed as a testament to the collective and evolving nature of scientific discovery. Thanks to these modern efforts, the secrets of the Antikythera mechanism continue to unfold, ensuring its legacy as a marvel of ancient engineering. Recent technical investigations into the Antikythera mechanism have provided amazing and instructive insights, thanks to cutting-edge imaging and computer modeling. These advances have allowed researchers to re-evaluate gear ratios and read ancient inscriptions with unprecedented precision. One notable discovery is the new estimate for the number of holes in the calendar ring. While earlier theories suggested 365 intervals corresponding to a solar calendar, recent evidence indicates that the ring likely contains 354 or 355 holes, aligning more closely with the lunar calendar used by the ancient Greeks. The meticulous craftsmanship of each gear is evident, with a number of teeth on every gear carefully calculated to reflect specific astronomical cycles. Advanced imaging techniques, such as computer tomography, CT, and high-resolution X-rays, have been crucial in these investigations. They allowed scientists to examine the internal structure of fragile fragments without disassembling them. The scans revealed hidden inscriptions and provided detailed information about the gear tooth profiles, leading to computer simulations that replicated the intermeshing of gears. These simulations confirmed that the gears were cut with remarkable accuracy, comparable to modern machining techniques, even though they were crafted by hand. However, simulations also showed that if the mechanism were to be operated in its current state, it might jam after several months of continuous use, likely due to corrosion and wear accumulated over centuries. The inscriptions on the mechanism offer additional technical insights, providing step-by-step instructions for calibration and operation. They mention specific cycles, such as the 19-year Metonic cycle and the 18-year Saros cycle, and confirm that the device was designed to track these cycles precisely. Enhanced imaging has recovered enough detail to show that the mechanism was calibrated based on clear mathematical principles, reflecting the advanced understanding of astronomy and mathematics possessed by the ancient Greeks. Furthermore, a thorough analysis of the gear ratios reveals that every gear was part of an intricate system of mathematically accurate relationships. These ratios ensured that, over a complete cycle, the positions of the Sun and Moon would repeat predictably. For example, the Metonic cycle predicted that after 19 years, the lunar phases would realign with the solar year. This sophisticated gear arrangement is evidence of the fusion of theoretical knowledge and practical engineering. The technical analysis of the mechanism challenges the assumption that advanced computational devices were only invented in modern times. Instead, it demonstrates that the ancient Greeks developed complex systems to model the heavens using only mechanical components. Modern engineers are inspired by this blend of simplicity and complexity, as it shows how basic components and creative design strategies can solve problems that still influence today's methods. The new modeling techniques developed for studying the Antikythera mechanism extend beyond this one artifact, as researchers now apply similar statistical approaches and high-resolution scans to various fields, including archaeology and materials science. The success of these methods in reconstructing the mechanism encourages further interdisciplinary research, ensuring that the Antikythera mechanism continues to serve as a symbol of the potential for cross-disciplinary collaboration in scientific discovery. The Antikythera mechanism serves as a bridge between ancient craftsmanship and modern technological innovation. Recent studies have revealed much about the sophisticated manufacturing techniques of its creators. Despite lacking modern tools, the ancient artisans achieved remarkable precision in their metalworking, creating gears with tolerances that suggest advanced knowledge of craftsmanship. Analyzing wear patterns and the microscopic details of the gears provides experts with a deeper understanding of how these machines were maintained and operated. Furthermore, studying the effects of long-term corrosion sheds light on the mechanism's original state, helping scientists piece together how it might have functioned before it deteriorated. The technical investigation of the Antikythera mechanism uncovers a striking level of accuracy and innovation. The gear's precise ratios, the clever use of a pin and slot system, and the recovered inscriptions demonstrate a design that is rooted in both mathematics and observational science. These discoveries challenge modern assumptions about ancient technology and underscore the lasting impact of Greek inventiveness. By combining advanced imaging, computer simulations, and statistical analysis, researchers have not only recreated the mechanism's operation but also enhanced our understanding of its production and legacy. But perhaps the most profound revelation is not just how the device worked, but what it represents, a glimpse into an ancient world where science, art, and engineering converged in ways still inspiring modern researchers. The legacy of the Antikythera mechanism stretches far beyond its function as a timekeeper. It has become a symbol of ancient Greek scientific vision and invention. Over 2 millennia ago, Greek craftsmen and researchers collaborated to create a device capable of predicting celestial movements, a remarkable achievement that holds up even by today's standards. This artifact challenges the notion that complex computational devices are a modern invention. The mechanism's intricately cut gears and detailed inscriptions reveal that the ancient Greeks had a deep understanding of mathematics, astronomy, and mechanics. Their ability to merge theory with observation led to the creation of a machine that could forecast celestial events such as eclipses and lunar phases, demonstrating a level of sophistication that influenced technological progress for centuries. Today, the Antikythera mechanism is showcased in museums around the world, with exhibits allowing visitors to interact with replicas and models. These displays not only educate the public but also inspire future generations of engineers and scientists. The story of the mechanism is one of persistence, innovation, and humanity's enduring drive to understand the natural world. Moreover, the mechanism has fostered international collaboration across various fields, from astrophysics to mechanical engineering, as researchers continue to analyze the surviving fragments and develop more accurate reconstructions. Their work, which blends ancient knowledge with modern technology, has led to groundbreaking discoveries that challenge long-held assumptions about ancient Greek science. The influence of the Antikythera mechanism extends to modern engineering. The principles behind its gear design and mechanical computation are studied as part of the history of technology, serving as a testament to the ability of basic mechanical parts to solve complex problems. For contemporary engineers, the mechanism is an example of how ancient inventors tackled challenges using simple tools and creativity. The lessons from the Antikythera mechanism encourage innovation by showing how